This is R2D Tech and we're back again with another video today, this time about how processors work, so stay tuned. Now, I'm not going to go into too much detail on everything because that would take a very long time. Some people do degrees on this. So I'm just going to go through the basics from the very beginning today. So let's get started. Now, you've probably heard that computer processors are made out of transistors. And you might have also heard that transistors are made from silicon, which is a semiconductor. However, what you probably don't know is that silicon is rarely used by itself. Chip makers use a process called doping, which is where impurities are inserted into the silicon to make it a better conductor so that enough current can actually flow through the silicon. There are two types of doping which are both vital when making processors. Firstly, there's N-type doping, where the N stands for negative. This is where most commonly phosphorus is inserted into the silicon, giving it an excess of electrons. If you've ever taken a physics class, you might know that electrons have a negative charge, and so that's what gives the silicon this negative charge. There's also P-type doping, which stands for positive. That's where most commonly boron is inserted into the silicon, giving it a lack of electrons and therefore its positive charge. The most important part of this, however, is that only when current is applied to the silicon can any of the electrons move. That's why it's called a semiconductor. So moving on, another very common use of these doped types of silicon is in diodes. Now, you might know that diodes only allow current to flow one way. The setup of a diode is as such, with a section of N-type doped silicon next to a section of P-type doped silicon with two wires coming out of each side. Now, the reason why current can only flow one way from the N-type doped silicon to the P-type doped silicon is because there's an excess of electrons in the N-type doped silicon and a lack of electrons in the P-type doped silicon. Therefore, when current is applied to the silicon, the electrons can only flow from N to P and not the other way around. This is also incredibly important when talking about transistors, because a transistor is basically two diodes stuck back to back. Now, talking about the setup of a transistor, you've got two sections of N-type doping on the sides and one section of P-type doping in the middle. You've then got two wires coming out of each side of the N-type doped silicon sections. You've also got one wire going into the P-type doped silicon section, which I'll call the control wire. Now, this all sounds really complicated, but I'll just say that basically, in order for current to flow from A to B, the control wire also has to have current. That is basically how a transistor works, and you can see that it's kind of like a switch. In order for current to flow, the control wire or the switch has to be enabled. So a transistor is basically just an electronic switch. The next step is to use these transistors to create logic gates. Now, logic gates are electronic components that allow us to evaluate logic, as the name suggests. They usually take two inputs in the form of current flowing through wires, which can be used to represent binary values. If current is flowing, it's a 1. If not, it's a 0. The logic gate will then give one output depending on what that logic gate was evaluating. So we're going to run through the most important and common ones. First up, we have an AND gate. This is a logic gate that will only give an output of 1 if both inputs are also 1. For example, if one of the inputs is a 1 and the other is 0, the output will also be 0. And if both inputs are 0, the output will also be 0. Only when both inputs are 1 will the output also be 1. Next up we have the OR gate. This is a logic gate that will give an output of 1 when at least one of the inputs was also 1. For example, if both inputs are 1, the output will also be 1. If one of the inputs is 1 and the other is 0, the output will be 1. Only when both inputs are 0 will the output be 0. Next we have the Xor gate, which is an incredibly important gate. It's a logic gate that will only give an output of 1 when only one of the inputs is enabled with 1. For example, if both are 1, the output will be 0. If both are 0, the output will also be 0. Only when one of them is enabled with 1 and the other 0 will the output also be 1. Next we have the NOT gate, and this logic gate actually only takes one input and gives the output as the reverse of the input. So if the input is 1, the output will be 0, and if the input is 0, the output will be 1. Those are all the logic gates that we really need to know. There are also a few others, however, they can all be created with the logic gates we've already been through. Next, we have to create what are called adders from our logic gates. Now, a single adder allows us to evaluate the sum of 2 bits or binary digits. Now, adding in binary is pretty similar to adding in base 10, which is what we all use in the real world. Let's say we're adding the numbers 53 and 19 in base 10. First, we would evaluate the sum of the rightmost digits, which are 9 and 3. The answer we get is 12, but we can't just write that down. We write down the 2 and we have to carry the 1 over. So evaluating the left digits, we have 5 and 1. So we get 6. However, we also have to add the carried 1, so the final answer is 72. This is similar to what's done in binary. Let's say we're adding the numbers 1, 1 or 3 in base 10 and 0, 1 or 1 in base 10. First, we see that the rightmost bits are both 1, so we therefore write down a 0 and then carry the 1 over. We then see that the left bits are 1 and 0, so we get 1. However, because we carried the 1 over, we then also have to write down a 0 and carry another 1 over. So the final answer is 1, 0, 0, which is 4 in base 10. Now, a single adder can only evaluate 2 bits. We have inputs of A, B, and carry in. We also have outputs of sum and carry out. So the clear limitation is that one adder can only evaluate 1-bit numbers. If we wanted to evaluate numbers with more bits, we would have to connect adders together, with the carry out of one adder connecting to the carry in of another. Now, if we wanted to sum 64-bit numbers, as most modern computers can, we would have to connect 64 adders together. This is what allows computers to evaluate incredibly large numbers. Now, connecting these adders together has basically given us the core of what's called the arithmetic logic unit, or the ALU. This component handles all arithmetic operations, and in my opinion, it's probably one of the most important parts of the CPU. When it comes down to it, most operations come down to adding, whether it's multiplication or subtraction or division. Multiplication is basically just adding numbers repeatedly, and division is basically just subtracting them repeatedly. Now, we've just built one part of the CPU, and there are so many others. For example, the control unit, the clock, the memory buffer register, and these are all really important when completing what's called the fetch, decode, execute cycle, which is basically the process where a CPU gets an instruction, decodes it, and finally executes it. However, that might just be a topic for another video, so we'll probably leave it there. I've left some links in the description if you want to find out more or go into more depth on each of the topics. However, that's it for this video, and if you liked it, please press the thumbs up button. If you loved it, please consider subscribing. If you also want to follow us on Instagram and Twitter, the links will be in the description.